Um, 9 a.m. on a Monday morning. I'm very impressed. Okay, hopefully you can see my screen. Okay.
Yep.
Thank you, smaller. Yeah, so it's really an honor to be invited to speak. I looked at the other talks and on the website there are a lot of exciting things going on. So as Daniel said, I'm mostly going to talk about recleansing. That's what I've been spending most of my time doing. I lead the group in DS, co-lead the group in DS with Judith Pratt. And I'm about to start leading the group in LSST desk, the recleansing and large-scale structure group. And that's kind of what this talk is focused on, is how we've gotten science out of these recleansing surveys like DES, the Dark Energy Survey, and what we need to do better, essentially, going forward with LSST. So recleansing is one of our most powerful cosmological observables. It has immense potential to probe the expansion history of the universe, to map dark matter concentrations. And beyond testing our standard model, it can also be used, as you'll see, as a tool for investigating galaxy formation on small scales. So it's really great on paper, but in practice, analyzing recleansing data is tricky, and mostly what I spend my time doing is, and especially during my PhD and my postdocs, was calibrating the data. That's really what I first tried my hand at for the first 5 years or so. And now I focus more on the modeling a little bit. But the field has rapidly changed in that time. I think that's what I enjoy so much about it. I did my first recleansing project coming up on a couple of years ago. And there was a buzz at the time about this groundbreaking experiment called CFHT lens that had measured recleansing due to the large scale structure from 9 million galaxies. And they constrained cosmological parameters and found slightly different results to Planck, and people were excited about it or had various opinions about it. And now, really, recleansers are about to be essentially fire-hosed with new data. The last decade saw these 3 surveys, the Hyper-Supreme CAM survey, the Kilo Degree survey, and the Dark Energy survey, churning out data in healthy competition, independent teams. So I did my PhD as part of KIDS, and then I jumped to DES when I started my postdoc, and now I'm actually working with HSC data since I'm at Princeton and DES. And as you probably know, we have this epic next decade coming. We'll shortly have billions of galaxies for recleansing from the Vera Rubin Observatory's LSST, the Large Survey of Space and Time, and Roman Space Telescope and Euclid Space Telescope. And so the game has totally changed. We have this high precision probe, and it's already giving intriguing results. And our real task is to understand those results, but also to control the challenges or the systematics that we're facing. And I'll talk a little bit about those today. So taking a step back, just briefly, what is recleansing? Well, the foreground distribution, the distribution of foreground massive objects are spatially clustered, and their presence, those overdensities, distort the fabric of the universe, so that when we measure the light from even further away, distant galaxies, the light path has been bent due to those distortions, and as a result, we observe our images of background galaxies to be slightly altered. They are also distorted. And galaxies whose light travels past the same structures of the universe, like the 2 galaxies on the left-hand side here, they acquire coherent distortions or alignments. So they're aligned and they're stretched similarly. Now, in moving away from that toy picture to jumping up to slightly more realistic, we have this simulation box in the top right, just another way of viewing what's happening. And there is large-scale structure in it. And the galaxies that we're measuring are the yellow toy galaxies in the back, and their light is distorted, their light path is distorted along its journey to the image plane in the foreground. And so what we're measuring is the correlation of shapes of galaxies which are distorted due to the intervening large-scale structure. So we're measuring the psi plus and psi minus, we call them, the angular, the auto and cross correlation of shapes separated by some angle theta. Now, to model our signal, we need to understand how far away the galaxies in our sample are. So we need to know how much lensing should we expect, how much large-scale structure has the light passed through. And in practice, we don't have a nice spectroscopic survey, so we don't have per galaxy redshifts. Instead, we measure the redshift distribution of the ensemble of galaxies. And in reality, we don't do this for the entire sample, but we take our sample and we bin it up into redshift bins, as I've kind of shown here. And we measure the autocorrelation within bins and the cross correlation across bins of these shapes. And the correlation functions that I'm showing here for just one bin and the best fit model, the correlation functions are directly related to the underlying structure of the universe, and it's particularly sensitive to omega matter and sigma 8, so the amount of structural clumpiness of the large scale structure. And the best parameter that we can measure in weak lensing is the cross here, which we call S8. So it's just a combination of those two parameters. And really, we see that degeneracy in omega matter and sigma 8. We can't tell if it's a lot of matter that's not very clumpy, or a little bit of matter that's very clumpy. So we've moved away from 9 million galaxies with the dark energy surveys year 3 analysis.
Sorry, Alex.
We measure. Yeah, go ahead.
Just a quick question. So this combination with the square root of omega matter is an intuitive way of seeing why the degeneracy, why that's a good combination?
Yeah, so this is because of this degeneracy, what we really can do when we get better weak lensing data is just squeeze that contour essentially. So we just traditionally lensing surveys have combined these two parameters and reported an S8. If you combine
why we combine it with a
go ahead.
With a square root, the 0.5 exponent of on the omega m.
That exponent choice is just traditional. Actually, if you change the redshift of your survey, so as we go to higher redshift, the degeneracy kind of moves along that plane. And we find already with DES and kids, for example, that that's not the best constrained combination anymore. But we just continue to report that. And we're going to have to think about that going forward, because LSST will be much higher redshift. And so we're going to have to change the exponent slightly again.
Good, thanks.
Yeah. And so if you combine your weak lensing data with BAO data, for example, then you get a nice constraint on sigma 8, but you need something to break that degeneracy between omega matter and sigma 8. So we moved away from 9 million galaxies. DESIA 3 was 100 million galaxies that we had in our sample, just over 100 million. And this is our data vector here. And it's just to show that it's a very large data vector. We have 4 redshift bins, and in the top left of each panel, you're seeing the bin combination. So this is the third redshift bin cross-correlated with the fourth redshift bin. And I've blown that up here, and you can see the lower panels are the residuals to the best fit. And really, the yellow is showing what we had in DESIA 3, the level of uncertainty of the signal to noise, and we're rapidly getting more data. So that's what the challenge, that's what's setting the challenge. Now, putting these observations into context for the whole picture that we have in cosmology, we're probing the late time universe. So with DS or Rubin, we're going out to redshift 1 essentially, and weak lensing is great for doing that. And we measure the amplitude of mass fluctuations in the current epoch of our universe. So very large density fluctuations in a universe that's now teeming with galaxies and dark energy, driving an accelerated expansion. And that's very different to what, for example, CMB measurements tell us. They're measuring the imprints of very tiny density or temperature fluctuations when the universe was in a very, very different stage. So Planck's, we often compare our measurements to Planck, which delivered this extremely high precision and exquisite map of the cosmic microwave background. And it really represents kind of the gold standard in lambda CDM cosmology. So Planck measured the density contrast of the universe as a function of scale, the matter power spectrum, and found this exquisite fit tau standard model. And so when we compare Planck CMB observations to weak lensing measurements, what we're really trying to do is test our standard model over cosmic time. So we have a really elegant end-to-end test of lambda CDM. And we're asking, can we use the same model that is so excellently describing the seeds of the universe to describe the vast structures that formed billions of years later? And that's kind of the name of the game that we play. We want to build up a consistent picture A standard model needs to describe a range of observations that span time. Now, as I mentioned at the beginning, GS aren't the only people in the business. We really shine in area. So I'm showing the footprints of the 3 ongoing surveys. Well, they've completed observations, but the 3 current surveys right now. So GS is this green area. We have the most area by a factor of 4 compared to kids, which is the next biggest, or 5 rather. And HSC is shown in purple, but don't be fooled by the smaller areas, because kids, which is the middle ground in area, they have excellent wavelength coverage. So they get 9 bands over the entire footprint. And that's really key for getting accurate redshifts. Whereas HSC is very small area compared to DES, but so much deeper that when we get 6 galaxies per square arc minute, they get about 15. So really these surveys are all competitive, and because the data is so different, we have different ways of analyzing it a little bit, different ways of doing our data calibration, and it's really compelling to compare our results. Now you can look at the results that each team has reported most recently, and so kids is in orange, DES is in green, and HSC is in purple, 2 different statistics, and we're comparing to Planck CMB here. And this, it has been curious and annoying that our results on this S8 parameter have been persistently low compared to Planck CMB, but not to high significance. People have a range of opinions on what constitutes attention. For me, it is very interesting that these 3 surveys work so independently, and we do our analyses blindly, and we all find such similar results. And they're all about 2 to 3 sigma low. I think a couple of papers have claimed 3 sigma from one survey. So it's very different to the Hubble tension, where there's where you can compare 2 experiments and they're hitting a 5 sigma mark. We just have this persistent trend that's been there since the first recleansing results, low S8. After we finished as year 3, a couple of us, Ami Choi and I, we were the only 2 people who were both in kids and DES. So we teamed up with Catherine Haymans and Marika Asghari, who lead the kids team. And, we had to start sharing what we find and sharing our way of doing things, which really hadn't been done before. There's no joint collaboration, cosmology. And so we teamed up and got the 2 teams to work together and compared our choices, and really did the most conservative analysis that we could think of. And what we find are these new pink results. And these are just different model choices that we can't really say which one is better or not. But I'll come to that later. But again, we found this low result, even when we really padded out our uncertainties. So what does this all mean? There's been a range of, there are various opinions on what this SA tension is. So here's one plot that's been shown a lot, where people have, about 10 years ago, people said, this is just a lensing thing. You guys just can't calibrate your data. I really think we've moved away from that now. It's very hard to explain these low results with an off calibration. I would like to, and I just don't see how we could do that given how well we can pin down our uncertainties on things like redshifts. So then it became, there started to crop up other low S8 results. And so this plot is shown really, really frequently. I really don't like this plot because I think when we compile these results, we really have to be careful about cherry picking or showing duplicate results from surveys. But it's certainly true that it's painting a picture that other probes and other measurements are throwing up low S8 results. So this is often pitched as early universe versus late universe, but you can ask other questions. So when I moved to Cambridge, I was working with Naomi Robertson, a postdoc, and we tried to ask different questions. So is it just a lensing thing? That plot obviously suggests otherwise, but is it a lensing and a clustering thing? So I won't go into this paper in too much detail, but we wanted to test the consistency of lensing and clustering. And we did that using BOSS and all 3 surveys. And what we found, there were a few oddities, but what we found is that there is an inconsistency between lensing and clustering if you look at it at face value. But our results were showing us that this was really being driven by the small scales. So if you looked at the large scales on their own, you had a much less significant discrepancy, and it's hard to tell because you blow up your error bars. But certainly it was very clear that it seemed very clear that it was coming from small scales. And it prompted us to kind of look further. So then I teamed up with George Estafew, who is one of the leaders of the Planck experiment. And the first couple of months were really a conversation, let's call it, of defending each component of the DES weak lensing results. And eventually we stopped arguing about whose measurements were wrong, and started just trying to put the pieces of the puzzle together. And so digging into what all of these different measurements were saying. So we tried to kind of clear the cobwebs, clear all there were many results that were coming out at the time, trying to clear and see what was there, what's really the pattern. So clearly Planck.
Sorry,
yes,
Alex.
Go ahead.
Yeah, could you go back to the previous slide, the figure there? So
yes,
the separation in blue and red, is this some kind of cut that you're making at nonlinear scales, or?
Yeah, you're right. I didn't explain this. So when we started to compare the results, we really had a picture drawn like this for months, and we were trying to pin each probe down into what redshifts and what scales it was probing. And I'll come back to this, but right now this is colored, but kind of arbitrarily by what scales you're seeing.
Yes.
Let's come back to the
okay. Actually, maybe just a quick follow-up, maybe.
Yeah.
So is there a Kmax? Presumably, there's some Kmax that they allow in the weak lensing analysis. That's in between.
Yes, I will come. I have a plot for that. I'll come back to that.
Yeah, I wait.
Yeah. So the trends that we started to see was that clearly Planck, which is in gray here, is in tension with lensing surveys. That's what you could see on the summary plot before. And so just here we're looking at the matter density and then the S8 parameter on the y-axis. CMB lensing agrees well with Planck lambda CDM. So Planck CMB lensing agrees with Planck. So you can see that the tightening of the contours in the orange here, and you could look at that differently by combining the CMB lensing with the BAO, for example. The clustering and redshift-based distortions, there are many different analyses looking at this now, reanalyzing BOS clustering data. And certainly the results as published by the BOS team are consistent with lambda CDM. And then there's been reanalyses using newer model choices. And we tried to show a range of them and test a range of them. But what we decided at the time was that there's kind of a little bit of a scatter in the results depending on what model choice you use. And certainly you could argue that they agree with both Planck and lensing. So we said, let's just put that on pause until we get new results from DESI. And we didn't consider CMB lensing. The CMB lensing cross-correlation results at the time were low and also giving a low S8. And we kind of just said, we don't really know what to make of that yet. And I'll come back to that. So when we started to look at the results and put them in context here, what redshifts, what scales, to us, the solution started to become obvious. And what we saw was that the best evidence for this low S8 was coming from weak lensing. And really, we wanted to just flip the conversation, or at least add another avenue to the conversation, that it wasn't just an early versus late tension, but perhaps instead it was a linear versus nonlinear tension. We always do this comparison of across redshift, but we need to test our standard model across scales as well. And maybe that's what was driving the low S8 results. So if you look at this is getting to Daniel's question. I'm showing the DES measurements again, but here I am filtering the best fit prediction, which is shown in black, by which scales are contributing to it. So what I wanted to highlight here is the K-scale sensitivity of weak lensing. That nice linear K of less than 0.1 information is shown in blue. So really, you get a little bit contributing to the very largest angular scales for psi plus and very little combination in psi minus. So there's very few angular scales in our measurements that are coming from the linear regime. We're highly sensitive to nonlinear information. And that is a power of weak lensing. It gives us a way of testing our model in a new way and looking for new physics in unique ways. But it's very challenging to build accurate models for accurate cosmology. Now, what George and I tried to do is come up with a solution for this. We proposed it's a non-linear solution, but we wanted to demonstrate that. So we made the simplest model that you can think of, which is just saying, okay, we played around with the lensing data and we tried fitting the lensing data, for example, fitting only the linear scales versus the non-linear scales. We tried fitting it with Planck cosmology, and you can do that in weak lensing and get basically as good a fit. And so what we hypothesized was, let's say that Planck lambda CDM is a good description on linear scales. Let's force that in our model, and then just have this free parameter that modulates the nonlinear matter power spectrum. So it changes the nonlinear power spectrum enough. What do you need? How much do you need to change the nonlinear scales, the nonlinear model, to get to be able to get Planck CMB on linear scales? So it's kind of the simplest model, but let's roll with it for a bit. So this AMOD parameter suppresses the nonlinear matter power spectrum, and you'd need to suppress it to get a lower S8. So that much was clear.
Sorry.
So yes, go ahead.
Just to make sure I understand. So you're keeping the shape of the nonlinear power spectrum the same, but you're just scaling the amplitudes with no K dependence, or is that?
Yes, yeah. The K dependence just comes in where linear changes to nonlinear, but it's a highly simplistic model. Yeah.
Mm-hmm. Okay.
So when we fit the lensing data, so again, assuming lambda CDM with some uncertainty on linear scales, and then letting AMOD modulate the nonlinear matter power spectrum, you get a best fit value for AMOD, and then you can use that to show what does the nonlinear matter power spectrum look like in that scenario. So I'm showing the results here, and the way I'm showing them is I'm looking at the ratio between the matter power spectrum, the total matter power spectrum, and the dark matter only, the lambda CDM matter power spectrum. So this is how much we need to suppress the power on small scales, on nonlinear scales, to be able to reconcile the lensing measurements with Planck lambda CDM on linear scales. So we did it first. In the first paper we did this with kids, as it was just what was public, and then Calvin Preston joined as a PhD student, and he reanalyzed DES in this model. So what you're seeing is that it's perfectly okay it works pretty well, or perfectly well, to make the lensing measurements agree with lambda CDM on linear scales if you suppress the power this much on small scales. And okay, that's great. Is this a smoking gun for dark matter? There are many models that do this, many dark matter models or massive neutrino models that do this. But obviously the trick is that we know that other things do this as well. We know that there are energetic and complex processes happening in galaxies, like AGN feedback, and that we can see in hydro simulations that redistributes the matter on small scales and suppresses the power spectrum. So what I'm overplotting now are predictions from some of the state-of-the-art simulations, like Bahamas is what we use most commonly in our weak lensing surveys and in cosmology, and that's bracketed by this solid black line to the dotted black line. So either we have some smoking gun here for dark matter, or the hydro simulations are substantially underestimating the amount of feedback that's happening in galaxies. We need more extreme AGN feedback. And so we don't know the answer to this yet, but clearly in order for us to really get at dark matter in weak lensing, to get at different dark matter models, testing them, we need to pin down what's happening with baryons, and to kind of claim that something more exciting is happening. Now, when we put out the first paper, we made this checklist and predicted what upcoming results that we were looking forward to, what they should see if the solution was this nonlinear effects, if that's really what was causing the S8 tension. So we said we knew HSC cosmic tear results were coming, and we said, okay, they've got to be low because it's another lensing result. We knew that there were going to be new CMB lensing results from ACT, which they did put out in Matt Madhavachal's work in 2023. And we predicted, we hypothesized that they would be in good agreement with Planck lambda CDM, and indeed they were. They're beautifully in agreement with Planck lambda CDM primary, Planck CMB primary, sorry. And then we knew that there were going to be new CMB lensing cross correlations coming as well. which the ACT team put out earlier this year. And again, we thought if this nonlinear solution is correct, they also need to agree with lambda CDM on linear scales, with prime lambda CDM, and they do. And so this model has kind of held to the test that will falsify it, which is good. We have data to falsify the proposal. And the next big one that we're really excited to see are the DESI clustering and RSD results. That is primarily coming from low redshift linear scales. And if they find a low S8, it kind of breaks this nonlinear solution, and we need to think of something else. So we have the data coming that will weigh in on this. The one that I'm obviously most anticipating is desk weak lensing, LSSD weak lensing. And so I'm going to change gears a little bit now to talk about how we can get the most out of weak lensing data that's coming in the next generation. Okay, so we have a billion galaxies coming at us, and this S8 tension is still there, and there's still lots of questions. And so we need to think, how can we make the most of this epic data? So LSST will span about 5 times the area of DES, 4 times the area of DES. And it will also quadruple the number density of galaxies. So it's just totally going to blow out the water what we're used to working with now. And it's this 10-year survey with a 3-day cadence. So just gradually over the decade, building up a deeper and deeper image or movie rather of our southern hemisphere. So in a very close, a worryingly close time frame, this year 1 data set will contain more than 1 billion galaxies. And when you know the camera's up and running, thanks to our friends at SLAC, I got to see it in the last summer, and it is very beautiful. It is just a giant, it looks like a giant Nikon camera. And soon it will be on the mountaintop, and we're very excited for that. So in weak lensing, there are a number of challenges. As I said, it's both in calibrating the data and modeling the data, especially due to the fact that it's probing nonlinear scales, so there are lots of astrophysical effects. I won't describe all of these today. I'm thinking of the time. But roughly, I'll just say what the challenges are. So for redshift calibration, we don't have spectra. We're just estimating the distances to galaxies using a few colors. And there's a lot of degeneracy between the type of galaxy and the redshift of a galaxy, especially when you're only looking at it in a few bands. So for example, as shown here, these are 2 different type galaxies at different redshifts. And if, like in DS, we only have RIZ, like in Y3, over our entire 5,000 square degrees, it's very difficult to tell the redshifts of these galaxies accurately, to break that degeneracy. For shear estimation, we're really never looking at galaxies like this beautiful spiral here. They're more fuzzy blobs. I'm actually not, I'm not so worried about this. We're actually quite good at measuring the shapes of galaxies very accurately. The challenge that's going to come is that we have such deep data that when we measure a pixel of light now, we're rarely looking at light coming from one galaxy. We have blending happening where we're always getting this summation of light from foreground and background galaxies in the image. So that's really a challenge for us. How do you work out how much lensing you should expect? Now on the modeling side, there's intrinsic alignments. So galaxies are intrinsically aligned, and that masks a cosmic shear signal. We assume, well, when you think about weak lensing, you're measuring the correlation of shapes, and you want that to be a cosmological signal, not an intrinsic signal, an astrophysical one. So we need to model that effect carefully. Why and how galaxies align with other galaxies, for example, in their tidal field. And baryonic effects, we've touched on that with the degeneracy with the S8 solution being something more exciting. It could be that we're underestimating how much feedback there is coming from AGN effects and suppressing the matter power spectrum more than we think. But right now, we really rely on hydrosimulations for estimating that. So I'll actually skip over the redshift calibration. I'll come back to that. But one test we did at the end of DES was just asking the question of what was killing our constraining power? What do we have to worry about most? Do we just need more statistics, or are there effects that we need to do better, more precisely account for? And what we found, so I'm just centering results here, and the green result is our fiducial result. And I tried turning off all of the parameters uncertainties in our analysis. So you obviously get a wrong result. These all shift around. But just how much can we improve our constraining power? And what we found is that the red line, the yellow line is when we fix observational parameters like uncertainties in our shapes or in our redshifts. And actually for DS, we are sufficiently calibrating our data so that it doesn't hurt our constraining power. We have small enough uncertainties on those parameters. And that's okay for DS. That kind of makes sense for DS because we're relatively shallow compared to HSC and definitely compared to LSST. So that doesn't mean that that's a solved problem. It just means when we have shallow data, we're pretty good at it. Now for the modeling, when we turn off our modeling due to baryonic effects or intrinsic alignments, we can do substantially better. So astrophysical effects are really just tanking our constraining power right now, and we need to understand them better. And so that's what I kind of started doing, shifting gears. It was a bit depressing to see this plot at the end of Y3, having spent most of my time on the calibration. I don't know if I should be optimistic or proud or just really sad about it. But I kind of shifted gears to try to think about how we can do better going forwards. I'm not talking about DES year 6 in this talk, but we are actively working on our analysis. And I say we, meaning mostly students in DES. So I'm highlighting some of the kind of superstars who are leading key efforts of this work here. They're all current grad students. And we are hoping to put out results by the end of the year. And so stay tuned for that. I can answer some questions on that, but I won't go into it much more. But what else can we do other than getting more data? So one thing that I really wanted to think about is obvious from the essay tension is could it be that we're missing our understanding, we're underestimating feedback effects? So Leah Bigwood is a grad student at Cambridge working with me, and she's trying to tackle this question. So it kind of has two parts to it. These are all of the simulations on the market, and when you talk to the galaxy formation folks, some of them are widely disregarded as being too extreme already. So Cosmology it doesn't reproduce, for example, the gas fractions that we measure in X-rays, and so people don't really think that feedback can be that extreme. But clearly there's a range of amplitudes and extents that these simulations predict, compared to, this is the total power spectrum compared to the dark matter only again. And so in DS, what we do, if we go back to that plot, I should have put another copy here of our measurements. There were shaded regions, and in DS we throw away all of our small scales because we don't know which simulation to pick. We say we're not going to try and choose, let's just toss all the small scale measurements. And so we pick a simulation and say, let's count that as an extreme scenario, our most extreme plausible scenario, and throw away enough data so that a bias due to that scenario is small. And there are other approaches, there are other models that you can use on the market since DES year 3, more recent models, and they all kind of rely on simulation. So there's HM code, and that relies, it's calibrated to Bahamas simulation. There's SPK more recently, an emulator, and that is calibrated on X-ray data, and also Bahamas itself as a simulation is calibrated on X-ray data. So methods, our models are informed by these simulations, and these simulations are typically informed by X-ray data. So there's kind of a chain effect here. And so Leah tried, she did the first kind of comparison of what do you get in cosmology, and in a mock analysis, how well do these new models perform, and how do they impact our results? So here's showing that if you totally turn off baryon feedback, which would be incorrect, you get this gray result. And if you use these 3 different approaches, 2 different models, and also a scale cut that's chosen according to a simulation, you get these fairly consistent results with each other. And we dug into these models a little bit more, and within each model, you could change the flexibility of the model. You can either increase the model space, so free up the priors essentially. You can step up in complexity, or you can, I didn't talk about BCM yet, I'll come back to that. Or you can, turn off the X-ray priors in this green model and just let the model be free. And what I wanted to hammer home on this slide is there's obviously a degeneracy, but we know that recleansing information is probing nonlinear scale. So it makes sense that the value of S8 that you get, as we're showing here in blue, is extremely degenerate with how much feedback there is. So if we put the Bahamas prior down on our results, we get the dark blue. And if you free up the model space, you get this light blue contour, which is very easy to get a higher value of S8. So we really have to be careful when we're modeling baryon feedback effects. We are directly modulating our S8 parameter. And we looked at how, when we analyze recleansing data with these models, what do you get for the power suppression? And the trend is the same, where if you use the constrained model, the more informed model, you get the darker colors here. And if you free the model space, it starts to prefer a more extreme scenario, the recleansing data on its own, but it blows the error bars. So we need something else to constrain it.
Sorry, can I ask?
Now,
Alex, sorry.
Yes, go ahead.
So in the tension plot that you showed at the beginning, what was being done there? Like
that is throwing away scale cuts, throwing away measurements. There are some slightly different model choices. So I'll come to the intrinsic alignment model. In all of these, we've used a different intrinsic alignment model to what we showed for DS in that first plot. And I'll come back to that because that is also changing our results in a concerning way.
Okay, thanks.
But the new strategy that we wanted to put forward was, instead of throwing away scale cuts dictated by a simulation or using a model that's calibrated on a simulation, why don't we use the most flexible model that we have, which for us is called BCMU, it's baryonification. So the model is made by moving particles around in a dark matter-only simulation to mock what feedback effects might do. But what we liked about the model is that it's been shown that it can reproduce a range of simulations. It can reproduce essentially many of the simulations or all that it was tested against. And so we wanted to use this most flexible model. And instead of throwing away data or calibrating it to simulations, we use this most flexible model and we jointly analyze it with some probe of the gas. And for us, we chose the KSC measurements. So the KSC effect arises due to Compton scattering by moving plasma, and it generates a signal in the CMB. And the measurements exploit the fact that if you know the bulk line of sight velocity, which you can get from a spectroscopic survey, then the KSC is directly measuring the electron number density. So it gives you a really good handle of the gas. And in particular, these stacked KSC measurements that were done by Manuel Shan, using ACT and BOSS data overlapping, ACT and spectroscopic SDSS data, they're well suited to probe the low density and low temperature outskirts of galaxies and groups. And so for the cosmologists in the room, if you what we liked about them is that the simulations are calibrated on X-ray data, which probe very inner regions and energetic, the most energetic regions, whereas KSC kind of lets us see a different view of feedback. So we did the first kind of joint recleansing and KSC analysis that includes all the whistles and bells that you need to do recleansing, just to demonstrate this point. Now, these KSC measurements are low signal to noise. They're the first stacks that are quite significant, but they're still only signal to noise of 7. So we're not expecting this huge jump in constraining power, but we wanted to start building the framework to do this kind of analysis because we will have better measurements very soon coming from DESI and ACT. Now, when we jointly analyzed our recleansing data with the KSC data, we get this purple constraint. So we get really great agreement with Planck. In this scenario, you still have a cost in precision by using this most flexible model, but you do get a slight shift in the results of S8. And so this starts to raise questions about the consistency of different views of AGN feedback. And I'm a cosmologist, but I've been learning more about this. Is it that we have this single view, or for what we care about in cosmology is this power spectrum, which is predicted from a simulation, and mostly it is calibrated on X-ray data. So are we missing some other view of feedback that's letting us see the outskirts, that's letting us see lower mass galaxies or higher redshift galaxies? And I'll come back to that point because we wanted to pitch the idea that we could use recleansing to benchmark the simulations. Now, the other worrying thing, which was kind of clear in that plot that I showed, and I alluded to already, is that we need to model the intrinsic alignments of galaxies. And right now there are two models that are most widely used for capturing this effect. So they're both, so the nonlinear alignment model is traditionally what's been used as NLA here. And that's what we used as our fiducial in KidsPlus-DES. It's not the fiducial model in DES, but here's the result when we use it. So both of these models are grounded in perturbation theory. And the TAT model is a superspace of NLA. So it allows for more terms. It goes to the next leading order effects, and it includes tidal talking terms. And so it's more flexible. It has 3 more parameters, so it gives you larger errors. But what's very clear is that when you use the different models, this is NLA to TAT, there is a shift in the value of S8 that you get up to about a sigma, depending on the survey. And depending on what scales you're using. So TAT always gives us a lower value of S8. And that's true in KidsPlus-DES here, it's true in DES year 3, and it was true even in DES year 1. And so this is clearly a problem that we need to pin down before we can do analyses with LSST data where these shifts will be even more significant. And so one route that my group, this paper isn't out yet, but one route that we've been trying is you can directly measure intrinsic alignments in spectroscopic surveys by just filtering on redshift so that any correlation you get is intrinsic rather than cosmological. And it's quite clear in those measurements that that red galaxies are aligned, whereas for blue galaxies, we've never observed them to be intrinsically aligned. And that's interesting because most of our weak lensing data are blue galaxies. They're not these red, big, bright galaxies. They're boring blue galaxies. So what we tried doing, Jamie McCullough, who's a grad student I started working with when I was at Stanford, and she's joining the group at Princeton as a postdoc in September. But what we tried doing was splitting up our cosmic share survey into red and blue and pitching, okay, well, let's use blue galaxies only and propose that if we can't solve intrinsic alignments, if we can't model them, and we still keep finding no evidence for blue alignments, then we just, it's kind of like doing scale cuts for intrinsic alignments. You're taking a sample that's IA pure, or IA free rather. And so Jamie's been doing this project for a long time now, because you have to, when you split your data, that means you have to recalibrate all of your data. So what people have done as a team, Jamie has reproduced for the red and the blue sample. And indeed, what we find is that the blue galaxies do give more stable values, cosmological parameters, when you switch between models. So we don't see the same big shift that we keep seeing in our surveys of like 0.5 to 1 sigma. Actually, when you use no IA, you get a higher value of S8 and a higher value of omega matter. So you get better consistency with Planck, and the no IA value is the preferred if you look at the chi-squareds, but really they all kind of give good fits. So we want to put this forward as let's just do blue cosmic share if we can't solve this problem. And before I end, I want to just flash some new opportunities of what we can do with weak lensing data. What can we do when we have billions of galaxies? I really think we need to start using weak lensing data as a probe of galaxy formation, not just cosmology. So going back to Leah's results with this, when we analyze the data with KSC, we can then constrain the matter power spectrum suppression quite well with this combination. So the pink is with weak lensing only with that very flexible model. And the purple here is when we jointly analyze it with the KSC. So it is intriguing that is giving us, it prefers a more extreme scenario for suppression, more extreme than all of the simulations. And this is the first analysis doing this, and there are lots of things that we think we can do to make it better, not just getting better data. So there is more work to be done here. But certainly the idea that weak lensing data can be used as a benchmark for the simulations is important, because right now we just take these power suppressions as a prediction from the simulations. For people, just for the if you're thinking more about astrophysics in your time, this is a different way of viewing the same problem. We use the same data, the weak lensing plus KSC, and instead of just constraining cosmology or what the power spectrum looks like, we looked at how the types of observables that we look at in simulations more often. So for example, the gas fractions as a function of mass, and the mass gas fractions as a function of active baryon fraction, and the mass gas fractions. And what we could see, that the kind of takeaway here is that the simulations, as shown by the black here, the X-ray data, or which guides the simulations, they are coming from very massive halos, so 10 to the 14 or so. Whereas we're finding that from weak lensing data, which can see lower mass halos, unlike X-rays, we want lower baryon fractions and lower mass fractions. And so we think that that's what's driving this preference for this more extreme suppression, and then therefore a higher S8. And I think the question is, can we test it? This is what we need to test against. Is this scenario realistic from the simulations? Is it compatible with other data? It's certainly true that the weak lensing plus KSE are a complementary view of what's happening to X-ray. They are lower masses, they are higher redshift, where what we're more sensitive to with cosmic share, and they are the outer regions rather than the inner regions. So we really want to dig into this a bit more. In a paper that's going to be out on Tuesday, we moved away from AMOD, and we've proposed, we should stop doing weak lensing where we throw all of our data into these cosmological parameters, because that doesn't show you the full range of scales that we're sensitive to. And perhaps the more efficient way of using weak lensing data is just to do kind of what the CMB does and reconstruct the power spectrum. So instead of just analyzing the data with the simple parameter, we've tried analyzing forecasts for LSST data year 1 and year 10, where we're just, instead of constraining cosmology parameters, we constrain the power spectrum in bins of K. And what we see is that if we can analyze LSST data well, which I think we will be able to, we get these beautiful constraints on the matter power spectrum. So here's just comparing to other surveys like Planck, and then there's some constraints from Lyman Alpha and from SDSS. And you can see that we'll have competitive constraints, and obviously what I've tried to hammer home, what's unique about weak lensing is that we're able to constrain the nonlinear matter power spectrum. And so just to demonstrate why that might be exciting is because if you consider non-standard dark matter scenarios, like here we've used a model from Vogt et al, which is based on Rogers et al, but where if your dark matter has a 10% axion component, they've made predictions for a range of masses, and we will be sensitive to that with LSST desk weak lensing, and so that's really exciting for us. And the last thing I wanted to flash, which I won't go into, is, but I spent a lot of time in Risa Wexler's group at Stanford, and she's imparted on me this infectious love of dwarf galaxies. And we talked about this and finally tried it out when I had already moved. But can we use these mega surveys, these mega photometric surveys, to pull out a dwarf galaxy sample and do weak lensing of those galaxies? So we know that dwarf galaxies are dark matter rich, and their mass profiles are sensitive to different dark matter models. So dwarf lensing measurements don't exist to date because, or not so high precision yet, that we're going to get better, because it's very challenging to pull out from photometric surveys these low mass galaxies and know that they are not really just far away high redshift galaxies. But we tried this new technique, which we actually use for redshift calibration in our surveys, to do that, and we think it's working pretty well. So this should be a box. It's a machine learning technique, and each of these are little boxes. And so this should be a box of low mass galaxies that the tool has extracted, and they do look low mass. So we pulled out different mass samples from the DES data, and we measured their weak lensing profiles, and we modeled these profiles both analytically and using simulations. And we think we have the lowest mass weak lensing signal to date. So this is a halo mass of 10.5. And we think from LSST and DESI, we'll get much lower masses. And so this profile here, this is showing the mass enclosed as a function of radius r. As we go to lower masses, these profiles are more sensitive to different dark matter models. And so we're really excited about the prospect of being able to constrain that. And so just to summarize, I've kind of shown you a range of things here, thrown everything in, of what things my group are thinking about. And as Daniel said, I am new faculty, which means most of the work is being done by these excellent people. But But so we think that maybe we should be thinking about our S8 tension in terms of linear versus non-linear, instead of early versus late universe, or at least keep that option in the picture rather than only tackling the problem in one view. And if it is that's the solution, it could be some non-standard dark matter, for example, or that the simulations are underestimating the impact of feedback. We're actively thinking about new strategies to do weak lensing and to tackle these things that are limiting our precision right now. And we're very excited about new ways to use the weak lensing data, like to reconstruct the matter power spectrum, to constrain as a probe of baryons or feedback effects, and to benchmark the simulations, and hopefully to do dwarf galaxy lensing as a test of dark matter. Okay, thank you.
Thanks very much, Alex. We have time for some questions online and also in the room, if there are any. Are there any questions online?
Yeah, I have a very basic question.
Okay.
So what is the non-linear effect that you were talking about?
So if we look at the matter power spectrum, so if we look at this plot, you mean what would be the non-linear effect that's driving the solution, or just in general the non-linear
definition,
effects?
the non-linear,
Okay.
the definition of, yeah.
So mostly when we measure cosmology, different probes of cosmology like the CMB, they are measuring the largest scales of the universe where the linear regime holds, and it's relatively easy to model. As you go to smaller scales, more complex things start happening. So even in a dark matter only universe, dark matter starts clustering in a non-linear way, and that's more difficult to model. We do that pretty well for CDM. But what's more challenging is that galaxies and baryons start playing a role. So complicated things happen in galaxies. And so when we think about what holds up, what bolsters lambda CDM right now, it is mostly probes of the linear regime. And weak lensing is coming in with providing non-linear information. So this is the linear matter power spectrum in black here. And the non-linear matter power spectrum, just due to the non-linear clustering of dark matter, is shown as the dotted line. And so we want to be able to test our universe at high and low redshift and on linear and non-linear scales, because clearly we need to stress test our model in a range of regimes.
Actually, maybe I can rephrase the question, because what's maybe slightly surprising is that baryonic feedback should play such a large role, given that baryons are kind of a subdominant fraction of the total matter. So you might, I guess
yeah, so
back of the envelope estimate of the percentage change would be somehow the ratio of baryon to dark matter density. So does that put some kind of sanity check on? Yeah.
So I guess it is 15% of the matter distribution, and we're measuring weak lensing at the percent level. So we need to know this pretty well. Yeah. But certainly all of the simulations predict that baryons distribute the matter and suppress the power spectrum. It pushes the matter out to larger scales and suppresses the power spectrum on small scales, on these scales. And so this is just compiling all the simulations that that people use and talk about. As I said, the red ones here are regarded as too extreme, as is illustrious here. But for example, this purple one is from Simba, which is a relatively new simulation, and so it's not disregarded. So, or I guess depending on who you speak to in the hydro simulation community. But yeah, they have a really important effect, and it's mostly AGN feedback. AGN jets are blowing gas out and impacting the clustering one.
Well, I guess here the effect is 30%, so you might think this is a bit large relative to the 15%.
Yeah, totally. So Flamingo is the most recent, or Millennium TMG. That's the green one here and the blue one, and they really want much less feedback. Yeah. So are we? That's exciting then, because maybe we are seeing something more than just not understanding galaxies. But really, if you can't decisively rule these out, we are in a bit of a pickle for weak lensing.
Yes. Okay, more questions. Yeah.
Sorry. Can you hear me?
Yes.
Okay. So I have a question about the you add the three parameters modify between the linear matter spectrum and power spectrum and the non-linear power spectrum. Can you go back to that?
Yes, I can. Yeah.
Yeah. So I'm confused about the left-hand side isn't that the non-linear power spectrum, the P sub n.
I missed the middle of it. I'm confused about
the P sub m equals to P linear plus some multiplication, and the P NL is P non-linear, right?
yes, exactly.
And you want to add the A modifier to modify it from the linear power spectrum to the non-linear. So isn't that the left-hand side is equals to non-linear power spectrum?
So when we measured, this is the matter power spectrum on the left-hand side, as in the total matter power spectrum, both the linear and non-linear information. And so what we're doing is we want to modulate only the linear matter powers, only the non-linear matter power spectrum, and preserve the linear.
So left-hand side is from observation, or it's a combination of the linear and non-linear?
So what, I'm not sure if is this the best way to answer the question. When we do our analyses, there are really accurate ways that you can model the linear matter power spectrum with things like tools like CAM. And what we do for the non-linear matter power spectrum, the non-linear dark matter power spectrum, is it kind of just modulates the linear even in our analysis. It provides a more accurate description on non-linear scales. And so we are just modulating that separate code. Is that what you're asking in practice? We are just modulating the non-linear part of it.
Okay.
I think you might be asking a bit about notation. If you set A mod equals to 1, then PM becomes P nonlinear. And so I think, yeah. Of course, the total...
Yeah, so if you had A mod of 1, if you had A mod of 1, there is no suppression. So that you would get no suppression, and you would have a universe that is well described by lambda CDM on all scales.
Okay.
Can I ask a question?
Yeah.
Sure.
Yeah, thanks for the nice talk. So it seems to me like you can increase S8 through baryonic feedback, and as well as if you consider nonlinear alignment model of intrinsic alignment. Is that correct?
Kind of. So for baryon feedback, if we look at DS, it's really true that if we allow for more extreme feedback, it's easier to get a higher S8 value. For the nonlinear alignment model, it does shift you to higher values of S8. But for example, if we go back, you can still have low S8 with NLA, is what I'm trying to say. So if we go back to the results from all of the surveys, so for example, the kids team already use the NLA model. So they have a low result even with that model space. Whereas we've used TAT in this scenario, and when we use NLA, we shift up about half a sigma.
Okay, so considering nonlinear alignment doesn't always increase S8.
It does always increase S8, but it's just better increases it enough.
Oh, okay. So it might be combined in real analysis or real interpretation. It should consider both at the same time.
Yes, or we need some better uncertainty. If we have two plausible models and they are giving you different values of S8, then you either need to prove one model wrong or put in a more uncertainty to reflect that spread. One thing that's clear is that NLA is not designed to work on the small scales that we're using, and neither is TAT. It does a slightly better job. And
Okay,
so
okay.
yeah, we need to just test these models better.
Okay, I see. Thank you.
And TAD is more theoretically motivated, is the argument that people who've come up with the model make, that this tidal talking term should exist beyond other things.
Okay, thanks.
Right, let me check if there's some last question.
Can I ask a question, Daniel?
Yes, go for it.
Okay, so can you talk a little bit about the discrepancy between the Lyman alpha and the lensing results that you show in the power spectrum?
Here, yes, okay. So you mean this plot, right?
Mm-hmm.
Yeah, so yeah, because it's like similar scales, I would expect some better agreement.
Yes, good question. So these are, well, so firstly, the purple are just forecasts at lambda CDM, at Planck lambda CDM. But the difference, you're right that here we're looking, in pink, we're showing Lyman alpha, which typically probe the same K regime as weak lensing, except it's at much higher redshift. So that when you're probing that K at that redshift, it's still linear. It's still linear theory. So Lyman alpha, it alludes to a good point, which is that we really want to span that full space of observations when we do cosmology. And Lyman alpha is an excellent way at getting the same K scales, but at higher redshift, where that K regime is easier to model in some ways.
Okay.
So even though they're, so this plot is showing the power spectrum when you project it down to redshift of 0. And then it's using the fact that at that redshift of Lyman alpha, that those K scales are linear.
Okay, cool, thank you.
Yeah. So really, if you want to get at nonlinear information, you need to go to much smaller scales at that redshift, or you need to drop the low redshift to get the same. Like we can do.
All right. Yeah, maybe we cut it here. It's late for you. And actually, I have to run to
Okay, yeah.
across campus. Thank you very much for this great talk. Some virtual.
Thank you for having me. Yeah, thank you. Take care. Bye.
Bye.